This is the last lesson in Unit 6 to do with exponential relations, and we're going to look at some problems involving exponential relations, exponential growth and decay. As you should know by now, growth is just a type of exponential relation that increases as time goes on, and decay is a type of exponential relation that decreases as time goes on. So in other words, picture the graph. Growth goes up from left to right in a curve, and decay goes down in a curve from left to right. Specifically like this. So this one's growth. This one's a little bit misleading. It shouldn't be quite so steep. A little bit more like this for decay. Okay? Those are just arrows pointing to them. There are many problems in science, medicine, finance for which exponential relations can be used as a model. True. Problem solving involving percents. So the first thing we want to look at is ones involving percents. If an exponential growth or decay problem involves percents, you must do the following. Change the percent to a decimal. Has to be as a decimal, absolutely. We have to add the decimal to 1 for growth or subtract that decimal from 1 for decay. Think of 1 as being 100% of something. In other words, if you had 100% and you changed it from a percent to a decimal, it would just equal 1, 1.00, or just 1, right? So if I want something to grow over time, it needs to be more than 100%. So 100% of something just means it stays the same. But say I had growth of 110%, that means it's going to get 10% bigger each time. So if I wanted 10% growth, I'd change that to a decimal, 0.1, add it to 1. So 110% would be 1.1. Or if I want something to get smaller, say I only want something to be 90% of what it was each successive year or day or whatever the time period is, then I'd subtract that decimal from 1. You'll see this in an example. Use the number obtained above as a base of the power in your equation. Okay, that'll be b in other words. In other words, this b right, sorry, find a different color, this b right here in the equation. Use the initial amount as a. All right. So first of all, let's work on getting the base. That's, in other words, getting b given different base situations. So if something is increasing by 10% each time, that's what I was just talking about. That means that really it's going to become, we want 110% of what we had before. So we start off with 100% of something. However much we have all of it, it's 100%. If it's going to increase, then it's got to go above 100% of what we currently have. So it's going to go up to, say, 110%. So an increase of 10% is now 110%. But our bases are always as decimals, so it would be 1.1. So in other words, we take that 110% and change it to a decimal and make it 1.1. If something's going up by 50%, then it's going to be 150% of what it was. But again, we need to express it as a decimal. Something increases by 100%, now we have 200% of what we started with. So in other words, it's doubling, right? If something increases by 100%, it's doubling, which makes sense that our base would then be 2. If we're decreasing, now we're taking that away from 1. So if we decrease something by 25%, how much is left? Well, 75% is left. As a decimal, that's 0.75. If we take away 50% of something, well, 50% is left. 0.50, or just 0.5 is good enough. If we take away 4.3% of something, we've got 95.7% of it left, which again, we need to express as a decimal. So in every one of these cases, this is our b value that we would put into the equation, okay? So we would, if we were making an equation, it would be y equals a, whatever our starting amount is, And then what I've just highlighted in pink, what we just calculated, would be the base of the exponent. Example 2. In a certain region, the amount of garbage collected was 1,000 tons in the year 2000. Okay, no problem. Due to recycling, now, this do is spelt wrong. It's the wrong do we got here, and that's going to bug me. D-U-E. That's the correct do. Due to recycling and composting, the people were able to decrease the amount of waste by 5% each year. Decrease, okay? Decrease by 5% each year. So that means that there's 95% left, which means that B equals 0.95 because we change it to a decimal. Write the exponential relation that models this problem. We also need to know the initial amount. Well, that was, what color did I use for that? I guess I didn't use any color. All right, well, the initial amount was this 1,000 tons. This is our A value. So if we put it all together, let's say W for waste equals 1,000 tons, our initial amount, times the base, 0.95, to the exponent T for time in years. Use this relation to determine the amount of waste collected in 2010. Remember, we started in the year 2000. That means that 10 years have gone past. T equals 10. So the amount of waste collected 10 years later, if it's going to go down by 5% each year, is 1,000 times 0.95 to the exponent 10. And that works out to be 598.7 tons. All right. In what year will the amount of garbage first decrease to half or less of its 2000 number? Okay, so again, in this case, what we need to do is we need to figure out, we want to find out exactly when half is. I mean, less would just be later. So half of 1,000 is 500, but we have to put that in for W. Okay, so W, in this equation, W is going to be 500, and then it's going to be 1,000 times 0.95 to the exponent T. So this is another one of these cases where we have to do a little trial and error, and we did this in our last lesson. So again, I can simplify it first. So I can divide this by 1,000 and divide this by 1,000 just to make the equation slightly easier. So what I get is 0.5 equals 0.95 to the T. And when I do that, if I do trial and error, just playing with the numbers a bit, it works out that somewhere between 13 and 14 years gives us 0.5. So, let's just try it again on my calculator. I want to put 0.95 to the exponent, let's say 13, and see if it's close to 0.5. 0.95 to the exponent 13 equals 0.513. So that's very close to 0.5. So that's about half, right? So that's, again, what we're doing. Half-life is another, this should be down here as a heading for this, is another type of problem we can look at. Radioactive decay is a process by which a substance made of unstable atomic nuclei changes or decays into a different substance. In this process, the core of an original atom or parent nucleus is split into two smaller or daughter nuclei. The time it takes for half of the parent nuclei to decay to daughter nuclei is the half-life. All right? So, for example, carbon-14 is a radioactive element. It's used to date ancient artifacts because it has a half-life of approximately 5,030 years. 5,730 years after the organism dies. The formula, unfortunately the Y got separated from the rest of it. I'm going to just tidy things up a bit here and put the Y over here. Y equals a times a half to the exponent x over 5730. That's the 5730 is simply, again, the time it takes for half of this carbon-14 to decay. And then that's what, and we want half-life. That's why our base is 1/2. And so then if we put a different x value in, then we'll be able to play around with this a bit until we figure out how old certain things are. A, of course, is always the initial amount. Y is the base of the power in the formula given above 1/2. Again, it's because 1/2, because half-life measures the time until only half the substance is left. If a sample from an animal bone started with 100 grams of carbon-14, how much would be left after the following times? Well, after 5,730 years. That's a strange number which sticks in my mind because that is the half-life. So I'd expect that after that amount of time, half of what we started with would be there. So I'm going to guess that 50 grams are left, but let's try putting it into the equation. Y equals A is our initial value, so we're starting with 100. A half was part of the formula. Let's move this A over a bit so I got a bit more room for my exponent. Then I'm going to put 5,730 over 5,730, and in case you're wondering where that came from, the bottom 5730 was just part of the formula up here. This top 5,730 was what was because of this. This is our x value, which goes right here. Well, anything over itself equals 1. So y equals 100 times 1/2 to the exponent 1. Anything to the exponent 1 just equals itself, so 100 times a half. 100 times a half equals 50, and as predicted, there are 50 grams left because that is 5730 is the half-life of carbon-14. Let's try some different numbers though. 1,000 years, so this is about 1/6 of the time of the previous example. So x is going to equal this now. So we're going to get the same equation. We're going to have 100 times 1/2, but instead of having 5,730 on top, we'll have 1,730 on top. Remember, this is all exponent here. I may not have written it. Actually, let me rewrite this. I don't want to change everything, but let's rewrite this part to make it look a bit more like an exponent. When you type all that into your calculator, what you get is 88.6 grams. So again, we started with 100 grams, and less time has gone by, so it's only decayed less than in this one. So this one with more time decayed to half. This one with less time didn't have as much time to decay as far. Whereas the last one here, 25,000 years, more time has happened for it to keep getting smaller and smaller. We're going to expect to have a lot less than 50 grams for this one because, again, the more time we have, the less we're going to have left of this material. So we're going to put, 25,000 on the top, 5730, and putting all that in the calculator and working it out, it comes out to 4.9 grams.